Greetings, everyone. We are Group 5, and our presentation addresses a major national challenge: traffic congestion at toll plazas, which has plagued commuters for decades. Our study, estimating vehicle arrivals at a toll booth to ease traffic congestion and enhance operational efficiency, is founded on the principle that congestion is not a random occurrence, but a quantifiable problem. We move beyond simply observing traffic jams to provide a data driven blueprint for a solution, one that tackles critical issues like commuter delays, excessive fuel consumption from idling, and the resulting disruption to commerce. This research links theoretical probability directly to practical urban transport planning.
The core problem we targeted is the highly random nature of vehicle arrivals at critical choke points like toll booths, which inevitably creates queue buildup. To model this randomness effectively, we selected the Poisson distribution, a time-tested tool in transportation engineering for analyzing independent random events occurring at a constant average rate. We base our analysis on a specific shoulder peak average arrival rate, which we call lambda, of 10 vehicles per 5-minute intervals. Our main objectives were first, to quantify the theoretical probability of high traffic overflow events, which we defined as K greater than 15 arrivals. And second, to simulate these events over a period of time. And third, to develop actionable operational recommendations that use this data to refine toll collection processes.
Our methodology began with a rigorous theoretical probability calculation using the foundation of curing theory. We formally defined an overflow event as the arrival of more than 15 vehicles in a 5-minute interval, a scenario that immediately strains the capacity and causes severe congestion. Using the Poisson probability mass function, we calculated the probability of this event, which we call P of x greater than 15, by calculating the complement. That is, we found the probability of P of x less than or equal to 15 by summing the individual probabilities from k equals 0 up to k equals 15, and then subtracting that total from 1. This crucial step provides us with the precise expected frequency of congestion based purely on statistical law.
To ensure our theoretical model was applicable in practice, we conducted a two-part simulation in Python. We first ran a simple 2-hour discrete event simulation over 24 intervals to provide a visualization of traffic volatility. More importantly, we needed to prove the model's robustness, so we conducted a massive 3-month validation test, which generated 25,920 data points. We then compared the resulting observed frequencies from this large dataset to the expected Poisson probabilities using a chi-squared goodness of fit test. This rigorous statistical comparison ensures that our simulated traffic accurately represents the theoretical Poisson distribution and is not a statistical anomaly, lending full reliability to our final conclusions and subsequent recommendations.
The results confirm the model's statistical accuracy and predictive power. Our theoretical calculation determined that the probability of a critical overflow event is 0.0487 or 4.87%. This is a powerful metric, indicating that a congestion event is expected to occur approximately 1 in every 20 intervals, or about every 1.7 hours. Crucially, the large-scale validation confirmed the model's fitness. The chi-square test yielded an exceptionally high p-value of 0.953. Since this p-value is significantly greater than the standard 0.05 threshold, we confidently failed to reject the null hypothesis. This result proves that our simulation is a statistically validated and accurate representation of the Poisson process. So for figure 1, we have the bar graph of simulated vehicle arrivals in 2-hour period. Here, we can see 3 occurrences of a traffic overflow happening at intervals 40 minutes, 1 hour 25 minutes, and 1 hour 40 minutes. Next, we have the frequency graph of how many vehicles arrive in each interval. So we have one occurrence of 16 vehicles overflowing in the toll plaza, and we have 2 occurrences of 18 vehicles overflowing in the toll plaza. And finally, for figure 3, we have a comparative bar chart that was used for the chi-square test. Here, we have 2 bar charts, one for the expected values calculated using the Poisson distribution, and one for the observed values run from the 3-month simulation.
Our analysis conclusively reveals that congestion is a periodic and statistically predictable event. Refusion the notion that is merely random chance. The 4.87% probability is the takeaway, providing transport planners a hard, quantifiable metric to work with the proactive mitigation strategies. Furthermore, the nearly perfect fit shown by the high p-value of 0.935 from the chi-square test demonstrates the simulation's high fidelity to the theoretical Poisson distribution. This validation fundamentally transforms the conversion around traffic from simply reacting to existing queues to proactively planning and investing in system capacity based on reliable statistical models and data-driven insights.
Based on our validated and predictable model, we propose a 3-tiered strategy to significantly increase lane throughput and build resilience against the confirmed arrival volatility. In the short term, we recommend deploying a dynamic, flexible lane system supported by a real-time alert system using sensor data to immediately open lanes and dissipate queues during predicted surges. For the medium term, the strategic focus must shift to an accelerated mandatory adoption of electronic toll collection or ETC. ETC drastically increases flow from about 200 to over 2,000 vehicles per hour, making the system fundamentally more resilient to the volatility confirmed by our model. Our long-term vision involves ambitious architectural and policy shifts, including mandating physically segregated ETC approach lanes to eliminate dangerous queue merging and rigorously studying congestion-based pricing to smooth demand and ensure the most efficient use of the roadway at all times.
In conclusion, this research successfully validated the Poisson distribution as the most effective framework for modeling toll booth arrivals, conclusively quantifying the overflow risk at 4.87%. This finding is a cornerstone of a data-driven approach to tackling the country's chronic traffic issues. Our structured, tiered recommendations, from immediate operational adjustments to long-term architectural transformation, provides a clear path forward. By implementing this blueprint, the Philippines can transition its toll plazas from passive bottlenecks into intelligent, flow-optimizing gateways, promising both enhanced operational efficiency and significant environmental benefits through reduced idling emissions. Thank you.